Hi everyone, my name is Kaiyuan Zhang, a PhD student from University of Washington, and today I will introduce Gallium, which enables automated software middlebox offloading to programmable switches. Recent progress in programmable switches have allowed developers to implement customized packet processing logic using the P4 programming language, which is an easy-to-use programming interface. It has been shown by various projects such as Silk Road and Netcache that offloading middlebox functionality to programmable switches can improve their performance and save CPU cycles. However, this still requires manual effort and a understanding of the switch model. Our goal in this paper is we want to be able to automatically offload existing middlebox implementations. To be more specific, we would like to offload part of the middlebox functionality to a programmable switch that is directly attached to the middlebox. We would like to use this programmable switch to perform pre- and post-processing for packets, and ideally, we would like to also find fast passes that bypass the middlebox server completely. There are several challenges regarding to how to automatically offload middlebox implementations. The first one is that we need to guarantee the functional equivalence between the offloaded middlebox and the original middlebox, because in the offloaded middlebox, the packet is handled by both the P4 program and C++ program. Therefore, we need to guarantee that when these two programs combine together, they have the same behavior as the original middlebox program. The second challenge is from the fact that there are multiple constraints of how we can program in P4. The first constraint is expressiveness constraint, which means that certain operations such as integer multiplication cannot be performed on a programmable switch. The other constraint is resource constraint, which means that the program written in P4 can only use a limited amount of resources. For example, the memory that can be used on the programmable switch is limited. The third challenge came from the concurrent execution of the programmable switch and the middlebox server. Because packets are being handled concurrently, this will lead to a different behavior compared to the case where the packet is only handled by the middlebox server. Therefore, we need to provide a run-to-completion semantic in the offloaded version to make sure that packets still appear to be processed by a single device. For the rest of this talk, I will first introduce the design of the Gallium framework. Gallium has three key components that address the three challenges mentioned earlier. I will describe them first before providing an evaluation of Gallium. The very first step of Gallium's offloading is to perform a dependency analysis on the input middlebox code. This is important because if none of the operations are reordered with its dependencies, the program behavior will remain the same. In Gallium, we consider two different types of dependency. Data dependency, where two operations access the same state and one of them is a write operation, and control dependencies, where the result of one operation determines whether the other operation will get executed. Gallium will generate a dependency graph of operations from the analysis and use it during the partitioning. Gallium's partitioning process will divide the middlebox code into three execution stages: the pre-processing stage, the middlebox server stage, and the post-processing stage. There are several constraints that we need to meet during this partitioning process. The first one is about dependency. Operations could only be placed on the same stage or stages after dependencies. This guarantees that operations have dependency between them cannot be executed in a different order. The second constraint we have to meet is the expressiveness constraint, which means that the offloaded stages, which is the pre-processing and post-processing stage, should only contain code that can be supported by the programmable switch. The third constraint we need to consider here is the resource constraints, which means that the offloaded code does not exceed the resource limitation of the programmable switch. To meet the requirement of dependency and expressiveness, Gallium will first perform a labeling algorithm that assigns labels to each operation. The label we use here is pre, post, and CPU, which corresponds to the three execution stages. The goal of the labeling algorithm is to determine when we try to satisfy the dependency and expressiveness constraints, where can each operations go. So the algorithm starts by initialize all operations with all labels. It then considers the type of operation being performed and remove labels accordingly. For example, an integer multiplication cannot be performed on the program switch, therefore its pre and post label will be removed. After that, Gallium will consider the dependencies between operations and remove more labels following the dependencies. In this phase, it will run iteratively until no more labels can be removed. After each operation is being assigned with a set of labels, Gallium then uses labeling information to determine where each operation should go. For operations of pre-label, it will be assigned to the pre-processing stage. For operation with a post-label but there's no pre-label, it will be assigned to the post-processing stage. For operations with only CPU label, it will be assigned to the middlebox server stage. After this process, each operation will be assigned to a single execution stage and therefore divides the program into 3 pieces. Now, after we obtain the initial partition that partitions the program into 3 execution stages, we will now need to consider the resource constraints and make sure that the partition satisfy with all these constraints. In Gallium, we mainly consider these following kinds of constraints: the total number of operations on a single execution path, the size of global states assigned to the switch, the number of temporary variables being used, and the size of actual header space required to transfer data from the programmable switch to the middlebox server. Gallium will use these resource constraints to perform a code motion operation, where Gallium will keep moving each operation from the pre- and post-processing stage back to the middlebox server stage until all the resource constraints are met. Now, after this, Gallium will generate 3 different partitions. Each of these partitions satisfy both the expressiveness and resource constraints. However, this is not enough to guarantee the correctness of Gallium's partitioning. Gallium will still need to provide a run-to-completion semantic. This semantic is important because in the offloaded version, the code is running on both the programmable switch and the middlebox server. This parallel execution between the 2 devices makes it possible for the programmable switch to observe a partially updated state when a packet is currently being processed by the middlebox server and therefore change the program behavior. In order to provide a run-to-completion semantic, Gallium used 2 different mechanisms. The first one is Gallium will buffer the packets and delay its release to network until all the updates to the switch states are being reflected on the switch. This ensures that packets with causal dependencies will always be processed using the most up-to-date states. The second mechanism being used by Gallium is that Gallium will batch all the updates to the switch state and perform all of these updates atomically at the very end of the packet processing on the middlebox server. This guarantees that the programmable switch is not being able to see a partially updated state. All of these 2 mechanisms is provided by Gallium as a runtime system. Now, the last step of Gallium's offloading is that Gallium will perform a code generation for all the 3 execution stages. For the pre-processing and post-processing stage, Gallium will generate P4 code, and for the middlebox server stage, Gallium will then generate C++ code. To evaluate how effective is Gallium's offloading mechanism, we perform a case study that uses 5 different middleboxes as input to Gallium, and we will see what is actually being offloaded and how much performance benefit can we get from Gallium. We first use 5 different middleboxes as input to Gallium and manually inspect what is being offloaded. We find that in all the 5 middleboxes, at least one of the lookup tables is being offloaded, and what's more importantly is that Gallium is being able to discover a fast path that bypasses the middlebox server in all 5 cases. We then evaluate the performance benefits of Gallium's offloading using both microbenchmarks and real-world workloads. Using the microbenchmark, we find that Gallium is being able to save from 21 to 79% of processing cycle to achieve the same throughput and can reduce latency by up to 31%. We also evaluate the performance using a more realistic workloads. We use the enterprise and data mining workload from the Conga project. We find that to achieve the same throughput, Gallium is being able to save from 3 to 81% of processing cycles. We also find that Gallium generally works better for longer TCP flows. This is because that in longer TCP flows, more packet is being processed by the fast path. There has been several previous projects that provide a framework for packet processing offloading. ClickMP will take a Click program and offload it to a FPGA device, and Flume will take a packet processing program and offload it to a programmer NIC that is programmed using the C programming language. However, one of the unique challenges of Gallium is that Gallium will take into consideration of the expressiveness of constraints due to the fact that the P4 language is highly restricted. So, to sum up, we introduced the Gallium framework, which can automatically offload middlebox implementations to the programmable switch. It guarantees the functional equivalence between the offloaded version and the original version. It uses both expressiveness and resource constraints to make sure the generated offloaded code can comply with all the restrictions of the programmable switch. It also provides a run-to-completion semantic to make sure that the parallel execution between the programmable switch and the middlebox server does not change the program behavior. We apply Gallium to 5 different middleboxes and find that Gallium is being able to detect fast paths in all these middleboxes. It can save from 21 to 79% of processing cycles and can reduce packet latencies by up to 31%.
Okay. So we have a few questions on Slack. So I'll select a few and ask them. So the first one, which is from Gianni Antici, is given the Gallium model that you picked, why switches rather than SmartNICs? Like SmartNICs seem like a more natural fit. Why the focus on offloading to switches?
So there are basically two concerns. Like the first one is that there are a wide variety of different smart NICs, and not all of them support a universal language. Some of them you can program using DPDK, which provide a more like Linux-like environment. Some of them you can directly program them in C, and some basically you have a customized SDK. And basically what we are trying to do is having a kind of universal interface. So we first have P4 in our mind, and then that's why we use a programmable switch. And I am aware that there are some smart NICs that have P4 support, but I don't think like we actually have that available to us at the time we developed this.
So then another question, which is from Hartek, who I think is from Cornell. How do you partition code in case of stateful processing? So I think the concern might be, how do you carry state through, or how do you track state or other things like that?
Yes. So in our in our execution model, we basically assume that all the state is accessible on the server side. So server can read and write switch state. And therefore, when partitioning, we basically characterize all the states into two parts. One is a global state, that is cross packet state. One is per packet state. And per packet state is basically local, basically stack allocated variables. And for global state, we detect them using static analysis over the CLIC code, because in CLIC, most of the global state are declared as class members. So we just do a static analysis and assume that's all the global states. And during the, basically, we will then do static and dependency analysis and partition these states into whether it can be all stored in the server side, or we have to store it on the switch side, and then the state is being partitioned.
So a related question, which is from Praveen, is what's the impact on performance due to global state that has dependencies? So he's worried that in run to completion scenarios, if you have two packets that are accessing the same or that are modifying the same global state, you end up with this dependency that should cause buffering or stall. And what is the worst case impact of this?
Well, it is slightly different. So remember that we basically use two different methods to guarantee a run to completion semantic. The first one is atomic update, which doesn't block future packets as accessing the same state. So you will be seeing an older state, but it is similar, or it is like equivalent to seeing a in-network packet reordering. And the other case, so the case we do buffering is that we need to wait until the state get updated before we release a packet to network. Therefore, if another packet have a causal dependency on this one, it will always see the newest state. So packets won't get buffered just because they have a data dependency between each other. It is only the case when you have a causal dependency, say a SYNACT packet that is in response to a SYN packet. In that case, we will actually need to see the buffering.
Sure. So I think there's some clarification that might help with that on Slack. And there's, in general, a fair number of interesting questions on Slack. So maybe you can help answer them there with that. Thanks.
Okay. So we have one question asked by Chen Sun. The question is, whether Gallium will introduce packet out of order. Since now the packet is processed both by the programmable switch and the CPU.
Yes, so this is exactly the problem that we are trying to solve by providing the run to completion semantic. So imagine in the case like in the case where another packet is being processed, while currently there is a packet being processed by the programmer switch. Therefore, what Gallium does is that it guarantees that you will always see a atomic update, which means that you will always see the result of before you process the packet or after you process the packet. It is possible in Gallium that we introduce we let the packet being processed by the programmer switch observing a older state. However, this is exactly the same as a packet reorder in the network. So a packet is received out of order by the middle box server. So yes, like this is possible, and we guarantee a semantic where it is equivalent to a out of order in the network.
All right, thanks. So I have a few more questions. So first, can you imagine that similar techniques can work for different programmable network backends? For example, various type of smart NICs.
Yes, I think similar technique in the sense of solving the constraints of expressiveness and dependency and using dependency analysis to guarantee functional equivalence is definitely possible to be used on other programmable devices. One reason we choose to use programmable switches instead of smart NICs, I think one of the reasons is that like smart NICs seems to have a more diverse like interfaces, and some of them have a more general purpose interface like C. Some of them, if I remember correctly, some of them even provide a Linux environment, so you can directly run DPDK on top of it. In that case, for that specific kind of setup, like the technique we're using here may not be that applicable to that kind of platform. So, but however, if we can find several smart NICs with similar resource constraints and have a universal programming interface like P4, then it is possible to apply similar techniques.
All right, one final question from this one is from Wei Bai. Can we extend Gallium to multiple programmable switches and multiple servers?
So when we designed Gallium, we didn't actually take multiple switch or multiple server situations into consideration. So I am not sure. Like because like one crucial thing about extending to multiple switches and servers is essentially you are trying to build a distributed system. Then it is unclear whether Gallium's guarantee that is targeting at a single server case will also apply to multiple server cases. The synchronization semantics scenarios will be much more complicated because now you will have to consider the existing synchronization scenario like in multi-server case, and then now you introduce multiple switches for each server, and then the synchronization between all of them will be much more complicated than what we have in our mind. So I'm not 100% sure whether the existing technique we have here can be directly used to say multiple switches and servers.